The magnitude of D is 13 units. Find the possible values of H. I know that for D, I'm supposed to move to the right by H units. H itself could be a positive, could be a negative value. Then I'm supposed to move downwards by 5 units. So when I do that, the magnitude is 13 units. So what was on the board was the magnitude calculation, right, using Pythagoras theorem. So our working is going to look like this. The magnitude of D equals to square root of H squared plus negative 5 squared. Okay, because 5 units downwards, we're going to square it, that gives us 25. So make H the subject. So H equals to plus minus square root of 144, giving us positive 12 or negative 12. Okay? So we've got other types of examples. ABCD is a parallelogram. Okay? Now explain whether AB is the same as DC. So you see, we are now trying to combine vectors with your shapes. In this case, quadrilateral or parallelogram. AB, this vector over here, is it the same as DC? Okay, why do you say yes? To say that two vectors are the same, there are two things you need to prove. First, they have the same direction. Second, they have the same magnitude. So in this case, are both fulfilled. One thing that's easy to prove is that they have the same length, right? Okay, size is the same already. What about direction? Are they in the same direction? How do you know they are in the same direction? Huh? How? What do you mean shown? They didn't show that they are parallel. Those are just arrows to indicate that they are vectors. Those arrows do not say that they are parallel. Because they already say it's a parallelogram. What is the property of a parallelogram? No, not all sides are parallel. There are two parallel lines, right? Two pairs of parallel lines. If lines are parallel, are they in the same direction?
No,
Is it?
No.
Okay, do you get my trick question? Okay, one more time. If two lines are parallel, are they in the same direction? For example, this line and this line, they are parallel. Are they in the same direction?
Yeah.
I can do this, right? Okay, this is a vector and this is a vector. Are they in the same direction? Yes, they are. But what if I do it this way? Are these two lines still parallel? Are they parallel? Yes, they are parallel. But are they in the same direction? No. Okay, so you must know this. When two lines are parallel, they may be in the same direction or they are in opposite direction. Okay, it's either the same or opposite for parallel lines. Okay, so for this parallelogram, very straightforward. We know that they have the same direction because it is a parallelogram, and we know that AB is parallel to DC. And because they asked for AB starting at A, ending at B over here, and starting at D, ending at C. Since the starting points, since the ending points are all on the right hand side of the starting points, we do know that they are parallel and they are in the same direction because both on the same side. So this is the reason for the magnitude to be the same. It's a property of a parallelogram. So two things to prove that vectors are the same. First, they have the same direction. So please highlight this. They have the same direction. Next, highlight. They have the same magnitude. Whenever we ask you to prove whether vectors are the same, you need to show to me that they are parallel. You need to show to me that they have the same, not parallel, they are in the same direction and they have the same magnitude. How you go about proving that depends on the question. In this case, because it's a parallelogram, very easy. Okay, and then the final conclusion is that hence AB equals to DC.
The magnitude is the line
Magnitude. Magnitude is the length. In this case, we take it as the length. Alright? Okay, so part B. Explain whether BC equals to DA. Where is my BC? BC and DA. Are they the same? So watch carefully. BC and DA. Are they the same vectors? No, they are not the same. Why?
Direction.
Direction is different, right? How different are the directions? The keyword is opposite. They are opposite direction. Are they parallel? Yes, they are parallel, but they are opposite. So, can they be equal vectors? Cannot. Magnitude same, but too bad, still not the same. I mean, overall, it's still not the same vector. Okay, so that is shown over here. So watch how they use the notation. Okay, they have opposite direction. Although magnitude of BC, you must be very familiar with how to write these kind of things. Although the magnitudes are the same, the vectors are not equal because direction is different. So they give you a further information that actually BC is the same as negative DA. Okay, why do they say that? Let's take a look at our diagram again. BC, okay, BC in green, negative DA. Negative tells us that the direction is opposite, yes? So DA looks like this, from D to A. Now if I go opposite direction, this is what I'm going to get. From A to D. Okay? Negative DA. Opposite direction. Then wouldn't this blue one be the same as the green one already? Right? This blue one is known as negative DA, which is the same as AD. Okay, starting from A, ending at D. Can you see that? The blue color one? Starting at A, ending at D. So if I change the letters, I put a negative in front, they are the same. We've done that practice yesterday, right? Change the letters position, put a negative, they are the same vector. Okay? Some of you look quite lost. X, Y is the same as negative YX. Okay, YZ is the same as negative ZY. Alright? Okay, example 4 don't need to go through, quite straightforward. Now, example 5. Here we have the vector PQ. It represents velocity. Okay, now it is no longer just about displacement. Now we see velocity being used as an example for a vector. Where does this vector start from? P or Q? P, ends at Q. Okay, find the magnitude of V. How to find this magnitude?
Find the vector.
Okay, Pythagoras theorem. How?
Negative.
So how do you write it? How do I write magnitude? Do you want to spell magnitude of V? No, okay, what is the shortcut? Okay, V, then the worm, and then 2 lines. So this is the magnitude of V. Some people will write this, some people will write PQ. Like this. The same, right? They are the same. Okay? Right. Now, what is the answer for the magnitude? Square root negative 3. Why negative 3? What is where going to the left? Huh? We are starting here, right? So you want to go along x-axis first, or you want to go along y-axis? X, right? So how many units to the where? 3 to the right. Agree, Sophia? 1, 2, 3. Do you agree? You want to start from below? Can. When you start from below, you mean this way? Is this what you're saying? No, you're starting from Q? Then you see the vector has a direction, right? You must start from P. So we are starting from P, we are moving to the right by 3 units. So this will give us square root of 3 square, then plus what? Negative 2 and a square, is it? Then a square root? Because negative 2 downwards, right? If I change this negative 2 to 2, does it make a difference? Doesn't make a difference. Okay, so all of you agree that this is the answer? All agree? This will give us 9 plus 4, which is 13. Yes? Then all wrong already lah. No? Magnitude will be positive. Magnitude don't have negative magnitude one. So what's wrong? Huh? Do you see it already? What is the... look, 1 unit represents 4 meters per second. Right? So, how many units do we have over here? 3, right? So this represents how much? 12. This represents 8. So it should have been 12 square plus 8 square. Or you can write negative 8 square, but it doesn't make a difference to our final answer. Okay? So 144 plus 64 is 188. Is it? One four four 64 208. Okay? Is square root 208 the same as 14.4? Is it the same? Same, huh? Okay lah. So this is how we do it. If you look at this example, they calculated in terms of units first. Then subsequently they changed the 1 unit to meters per second. They just multiply by 4. It's the same thing. Okay? Then there's a part B. Describe the direction of V using bearing. I hope you remember your bearings. We start from the north. We always need to know where the north is. Then we go clockwise or anti-clockwise? Clockwise. Okay. Where do we start from? So I draw the arrow at P. This is my north. Then I need to go clockwise, right? This is my bearing. What is this angle? How to find this angle? No? Cannot use protractor? How about you tell me whether it is greater than 90 or not? It is greater than 90. Where is my 90 degrees? 90 degrees is here. Right? This. Describe, meaning they want you to find the bearing. Tokaso? How?
No,
Correct angle or
no,
not?
that one 90, right? Then after that one is like half.
Half cannot. It's not exactly half. I want exact answers. How? Huh? You mean find this angle?
That one.
Which one? Which one?
Three.
You mean this angle?
No.
Then which angle?
That one.
What, this one?
No.
Still which one?
You draw like one line above the Q.
One line below the Q?
Above.
Above?
Then like,
You can find this angle, is it?
this 45.
How you know it's 45? No, who said it's half? If it is 45, it should look like this lah. Get it? That's 45 lah. Okay, so how to find the angle? I want the blue angle. Okay, Tokaso how? Tokaso I need right angle triangle. Where's my right angle triangle? Draw myself, is it? How? Like this? Okay, then I get this angle, right? Then over here I've got 8. Over here this is 12. And then what?
Okay. And
Tangent.
8
Let's call this theta. Theta equals to 8 over 12, which is 2 over 3. Then what? Theta equals to? Tangent inverse? 33 point what? 690 degrees. Are you in degrees or radian mode for your calculator? Make sure. So this gives us 33.7 degrees. Then we add that to 90 degrees, right? So the bearing equals to 90 degrees plus 33.7 degrees to give us 3.7 degrees. Up. Okay, textbook gave you another way of doing it, but if they are equivalent. So now your turn is to try it 5. Try 5 now. Okay, so scale drawings are just like that. Next, we have translation. Have you heard of this word before? Translation? In a mathematical sense. Translation? Is it primary school? You moving an object a certain way? No? Never heard before? Okay. Hey, but the textbook says we have learned the translation of the object. So you all learned before already? Okay, never mind, now I tell you. It is a transformation. What transformations do we know besides this translation? We know how to scale. For example, this square, we can enlarge it, right, with a scale factor, so I can make it bigger. So you'll end up like this, for example. That is stretching, scale drawings. This is a type of transformation. Another type would be maybe something like this. Then, after I transform it, it ends up like this. What is this transformation called? Huh? Starts with R. Reflection. We reflect it. So it's a transformation. Now this is another type of transformation. This transformation is called translation. It moves every single point of the object the same distance in a specific direction. Example. If I have a square over here, I am going to translate this square 5 units to the right, for example. So it will be shifted over here. So I translate it to the right. Alternatively, I can translate it upwards by 3 units, for example. Then I translate it over here. So translation is not stretching, it's not compressing, it is not reflecting. No, it is just moving the object somewhere. Okay? Can you imagine how vectors come into play now? Because vectors gives you direction and magnitude. Okay? So the distance in a direction can be described using a vector. So for example, if I want to move this square 3 units to the right, 2 units up. So you end up here, right? So this vector over here will be known as 3, 2. Get it? So if I say, this is my original box, I want you to translate it 3 units to the right, 2 units upwards. That is a vector given to you. You draw the vector, and you can get a position. Okay? So let's look at what we have. Here I have A, B, C, that is the original triangle. Okay, we've got point A, point B, and point C. It looks like coordinate geometry, right? For my X and Y axis, I've got points that join up to be a triangle. It is translated to DEF. So this triangle is not translated to this triangle. You can obviously tell that it's been shifted. Did it rotate the triangle? Do you see a rotation? No. It is just move to the right, then move upwards. Okay? And use this column vector to describe the translation to DEF. Okay. Where did this point A go to? Where did point A go to? Huh? D. Okay. So it went this way. How many units to the right did it go to? 1, 2, 3, 4, 5, 6, 7. Am I right? 7 units to the right. Okay, then how many units up did it go? 1 and 2. So from A to D, that is a vector, AD is 7, 2. Yes? Okay, so you can write that down. AD is actually 7, 2. What? What did he say? Everything will be the same. Yeah, he's right. Everything will be the same. If you look at B, it moved to E, right? How many units to the right? 1, 2, 3, 4, 5, 6, 7. And 1, 2. It's the same. CF is 7, 2. Likewise, BE is also 7, 2. So this fulfills our definition of translation. Every single point is moved. Every point is moved the same distance in the same direction. Okay? So in our triangle, every point moved 7 units to the right, 2 units upwards. Okay, and by joining the points, this is what we have. So the answer is 7, 2. Of course, you can do part B, and you will see that it is actually 6, negative 3. So now, try it 7. Just do it yourself very quickly. Choose a point that you want to translate. Here, we've got DH, which is the vector, the column vector for the transformation. It's negative 5, 3. You can do the same for any other point, as long as you match it to its corresponding point. So now try part B by yourself. Your homework questions will be question 5, 7, 9, 10, 14. Okay, 5 questions. I will go through them during our remedial session tomorrow.